This section does not have an activity that goes with it, but there is a lot of information in this section that we will be using throughout this entire unit on statics. Statics are the study of forces and their effects on a system in a state of rest or uniform motion. Rest means not moving. Uniform motion, easiest way to understand uniform motion is to think of something that moves the same way every single time or all the time. Static principles, to go over a few of them. So Newton's first law of motion, which is his law of inertia. An object that is in a state of motion or rest will continue to be so until acted upon by another force, what they call a net force. So you have a force that's greater than another force, which we'll talk about here in a moment. Newton's second law of motion is the acceleration of an object is proportional to the net force acting on the object and inversely proportional to the object's mass. Easiest way to understand Newton's second law of motion is to know that force is mass times acceleration. When we were talking about weight, we talk about easiest way to think of weight is the way we think of it in this country. We talk about pounds. Well, pounds are the mass that you are times the acceleration of the Earth's gravity, which is 9.8 meters per second squared. So weight is a force because of what happens to it. Newton's third law of motion, for every action there is an equal and opposite reaction force. Static equilibrium, equal means stays the same. Static is what we're talking about here with forces and how they act on objects. So a condition where there is not a net external force acting upon a particle or rigid body and the body remains at rest or continues at a constant velocity. So if you throw something in space, it's going to keep moving at whatever rate you threw it at until another force causes it to change. If you're driving your car, you hold the gas pedal at the exact same spot, it goes just as fast until you either go up a hill, which you have more gravity pulling you down and slowing you down, or you push on the gas pedal, which gives you more force out of the engine to move the car. Translational equilibrium, the state in which there are no unbalanced forces acting on a body. So if we look here at this bridge, balanced means it's all sitting there just fine, not a single problem at all. Everything's equaling out, you don't have any issues. Unbalanced, and you have a bridge like you see here that has just completely collapsed. Something was unbalanced somewhere. You had more force in one direction, going with gravity probably, than you did in any other direction. These two equations here are ones we're going to see quite a bit. Sigma f of x is the sum of all the forces in the x direction. They all have to equal 0. This is the sum of all the forces in the y direction, which is our up and down direction. Those have to also be equal to 0. Rotational equilibrium, keep in mind rotation means it's a spinning. It rotates. So the state in which the sum of all the clockwise moments equals the sum of all the counterclockwise moments about a pivotal point. So in this case, all the motions with the blue arrow need to be equal to all the motions with the red arrow. So sum of all the moments, big M stands for moment. We talked about moment at the beginning of the year. We talked about torque forces and rotational forces. So here they even have the formula. So the moment is the distance times the force. Static principles, scalar quantities, a physical quantity that has a magnitude only. For instance, mass, length, time, volume, temperature, pressure, speed, height, any of those, distance, those are all just scalar amounts. It's a set amount. It's 40 decibels when you stand right next to a car. There's 30, you're moving at 30 miles an hour. They're all scalar quantities. They're not telling you which direction it's going, up or down, or left or right. When we look at vector quantities, it is a physical quantity that has both a magnitude and a direction. Keep that in mind. So if you're going 40 degrees south and moving at 30 miles an hour, so you're 30 miles an hour at 40 degrees south, that's your vector quantity. Position, velocity, force, and moment. These are all good examples of static principles and vector quantities. What is a force? The pushing or pulling interaction of objects. A vector quantity tells you the magnitude and the direction. In addition, you also have to have the point of application. In this case, it is A. So we need to know that A is where that 45 pounds foot of force is going, 21.8 degrees northeast. British system of units, pound force is how we talk about it. Newtons are the international system of units. You're going to be given problems going in both directions. So it's best to know now that 1 foot-pound is the same as 4.448 newtons, and that 1 newton is the same as 0.2248 foot-pounds. Forces always occur in pairs. You'll see a lot of blue and red arrows. So if I have a force coming down, I need to have an equal and opposite force coming up to have no net force. If I have a force going to the right, I have to have a force going to the left that is equal and opposite to counterbalance it. So force pairs act in opposite directions and they have the same magnitude. Force components. This is where you really start seeing a lot of how this really helps out engineers and how we're able to find out where forces are really coming through. So a single force, in this case we have F sub A, can be replaced by component forces, or the forces that would make them up. So it's the same as saying I have a force of A sub Y going straight up this direction, and then I also have a force of A sub X going in that direction. And that's because this vector is going up and to the right. So I have to have an X and a Y vector. Either for Y it's up and down, or X it's left or right. Well, in this case, you can see that which direction it has to go. Resultant force, a single force that has the same effect as 2 or more concurrent forces. So the resultant force is the adding of 2 different forces, in this case 5 foot-pounds and 2 foot-pounds. The resultant force in this instance, 5 foot-pounds, and I have an opposite force of 2 foot-pounds, so my resultant force is 3 foot-pounds. Not a lot of new information, just a lot of vocabulary, knowing how we're going to apply things. When we get started with centroids, you're going to start seeing how distances and magnitudes and vectors really come into play.